my second time here, and however, I do see a lot of new faces, so I have to back up a little bit. So what I showed last time was a proof of concept flight that we had done a couple of days earlier before this conference, where we put one of our HDL32 LiDAR devices on an octocopter, went to San Diego, to the football stadium there, and we flew around the football stadium and took that point cloud. And last year I showed that video. I kind of assumed most people have seen it, that's why I didn't bring it this time. But actually a lot of things have happened in that 1 year. Well, it's not even a year, it's less than 12 months. So at that point, we're at that point of proof of concept flight where we're showing the point cloud. And by now, actually, I want to show you some more customer applications that have established since then. And people that are not familiar with LiDAR, well, LiDAR is a measurement technology that's used for measuring 3 distances. Essentially, it's a distance measurement. When you see the guys out there, actually on the construction site, I saw one, you see the guys with the tripod and they're doing these measurements of the streets. That's what LiDAR is. You send out a laser pulse, the pulse goes out, it gets reflected from a surface, it comes back, and the time that it takes to go that distance back and forth, you can determine the distance from the speed of light. Well, the trick that we do is we don't do it with a tripod shot by shot. We actually have 32 lasers in this device that are spinning, and we shoot those 32 lasers very, very fast to generate 700,000 measurements per second. So mounting this on a UAV, you fly around, you get 700,000 points per second. The lasers are oriented in a vertical array, assuming you have mounted the sensor like that. So you have 32 lasers on top of each other, with a 40 degree vertical field of view, and it spins around 360 degrees up to 20 times per second. So you get a full 360 degree view, and the 700,000 per second. It's relatively small. It's a size a little bit larger than a Coca-Cola can, and it only weighs 1 kilogram or 2.2 pounds, which is ideal for flying on UAVs, at least if you have a certain size of a UAV. Yeah, I think that's the main points there. The sensor can be mounted vertical. This would be ideal if you want to scan a building, like the stadium. You want to get the side of a stadium, but it can also be mounted in any orientation. So you can mount it in the horizontal if you want to look down, like typical aerial mapping is done. Velodyne itself, mentioning the word mapping. So far, our biggest business, actually the most famous one, is the Google self-driving car, which uses a slightly larger version than that. But there's a big business on mobile mapping where people put these sensors on cars and drive around. Like companies like Nokia, Navtec, they have about 150 of these vehicles and drive around all over the world, similar to Street View, to map the world with cameras. But in the background, they take LiDAR data to have 3D information for the environmental model. Okay. So that's the introduction. We're a little company. I'm from Germany. My name is Wolfgang. I have lived here for 12 years now. The company Velodyne is down in Morgan Hill, which is about an hour south from here in the direction of Gilroy. The company that I showed the proof of concept with last year is Phoenix Aerial Systems. They have not moved on, but they have developed their system further. It was a proof of concept first. Now it's actually it's a real product. It's a second version, so the Aerial LiDAR 2. And what that looks like in detail, you can see here. So a couple of changes in their concept. One is it's actually now a nice little square box. Let me get my pointer. A little square box that our sensor is mounted to, and what's inside that box is GPS and IMU and data storage. That's a little black box here that the sensor is mounted to. And then you can use this box with the sensor attached to it and mount it to your UAV. That could be an octocopter, or in this case it's actually a gasoline-powered helicopter. It could be all kinds of different UAV platforms that this system can be mounted to. And then, of course, in this case, it's mounted horizontal because the focus in this case was to look down. Phoenix Aerial System also has teamed up with a company called LiDAR America. The name is a little bit misleading because actually the main target market for LiDAR America is in South America, and this is where they're all present. And currently they're offering service flying of manned LiDAR systems, and the new offering will be to to also offer services based on UAV LiDAR. And obviously here's the helicopter with the thing, and yeah. To show you a little bit of what that looks like when it's flying, this is a relatively new video and it hasn't been edited, so I apologize for the roughness of it.
Rubber on the bottom, because when you
turn that sound off. So the sound is working, I just turned it off because there's a lot of background speaking. It's, as I said, it's not edited. So you can see the helicopter there, you see the scanner in the front with the box with the IMU and GPS. And of course the GPS and IMU is important because the sensor itself takes relative data to the sensor. But you still need to know where the sensor is and how it's oriented to put the data that's been collected all together and generate a big point cloud that comes out of that. This is the one where it's actually taking off. And of course this sounds a little bit like a lawnmower, but I guess it has the advantage of you can run it longer than just on batteries. The pilot and the cameraman didn't really agree on where he's going to fly, so he's going to disappear into the sky, and I'm sure you have seen all of these flying. But I don't have the point cloud from this data yet. That will be next time. I want to introduce another company that has been using our sensor, integrated it. It's called Wolf Photonics. They're on the East Coast here in the United States. They're known for hyperspectral sensors. And what hyperspectral sensors are is they basically analyze the lights with respect to wavelengths from the surface that it comes back from to make conclusions about what materials are in that surface. So this could be used for flying over an area where you might think there might be diamonds or gold, and you can establish certain chemicals in the ground or in the water that are precursors or somehow related and might be indicative of having these minerals in the ground. And obviously diamonds and gold is just one example, but those kind of things. And as an optional offering, Headwall, which is a company that's 16 years old and a spin-out from Agilent, Hewlett-Packard, they have now an offering where they include our LiDAR device, and they have put it on this infinite JIP UAV platform, and this is what that looks like. So this is their setup. So here's the sensor. It's mounted on a rotational gimbal, which allows them to actually change the angle on command. So they can fly out with the sensor in the upright position, and then while flying, you can actually point it in the direction that you want to point it at, and also ensure that when you land again, it's not necessarily in the most exposed position, but it's upright again, so in case there is a rough landing, that you actually don't damage any of the sensors. There's the hyperspectral camera here, there's our sensor, there's a GPS and IMU, and of course there's data storage. And what we scanned when we did our test flight there, what we scanned was, we put a couple of ladders on the ground here, and that you can see here, and some wooden boards, and then of course you have the natural features like the bush and the grasses. And what you see down here, that's the real-time LiDAR data that comes out of our sensor. So this is not georeference, this is not the nice point cloud that you want to get at the end. This is really the live data that comes out of that sensor in real time, the 700,000 points per second. And the lines you see, that's essentially each laser beam rotating on the bottom and making that reflection. You can clearly identify the ladder here. The boards are in this video, in this slide are not that easy, but here you can see the, this green strip that's here that has a different altitude, and you see different features, and if you spend a little bit longer, you can actually recognize each of these features in that live image. So, obviously you want to see the thing flying. The UAV manufacturer is up in Toronto, in Canada. Here again is the different components of the system. And here you see the target ladders, just to have some structure in the picture to see what it looks like, what can be scanned. So now is that rotation. So the scan set scanner is being moved from the vertical position to the horizontal position to look down. So this is what the test range looks like. And of course the live data out of our viewing program. It's a little bit dark here. Because that's not ideal with a room that has a lot of light. You can see the ladder here while you fly over it. And as I said, this is the non-georeference data, this is the live data. Of course, if you store all of that and put it in one big point cloud, you get an excellent model. You can take measurements on how wide the ladder is, how tall it is, how much it sticks it out. And the accuracy of our sensor is about plus minus 2 centimeters. And then, of course, in addition, you have the accuracy of the GPS. So you end up with about 5 centimeters accuracy. And then for landing, as I said, it's rotating back to the horizontal position so that in worst case, if the landing is rough, the sensor isn't being damaged. Yeah. Another company I want to mention, this is, we're not just selling systems here in the United States or in South America. Another company is iBotics. It's a company out of Germany that makes hexacopters. And they actually recently have been purchased by the mother company of Leica Geosystems, which Leica is one of these companies that makes the systems that's outside to measure construction sites or mining areas. And I'm sure that's where their main target area is, to sell this to mining customers. So instead of having airborne LiDAR, they can do this on a daily basis, fly around their stockpile, measure volumes, or look how deep the hole is that they dug on that day where they got the minerals out of the ground. And they have integrated our 32, and here's a video of their promotional video. In all true confession, not all of the data you see in there is actually made, not all of the data in that's in this video is actually been done with exactly that configuration. They took a little bit of a marketing license. But it's still very interesting. Obviously, their claim to fame is this special construction of the frame so that you, when you hit a wall or something, you don't break your propellers. Also, from a safety point of view, it's a little bit more difficult to get a finger into the propeller. It's mounted on a gimbal. In this case, the gimbal was fixed, but there's no reason to have the gimbal not moving it from any position vertical to any horizontal position. For example, this data, it says create indoor models. Obviously, if you do create indoor models, you have to think about the GPS. IMU still works, but GPS doesn't work, so you have to do something about that. So I don't think that actually has been really realized. That's more of what they want to realize. But you can see power lines with our system when you fly on them, when you generate these point clouds. And even so, the data is taken from the top because it's a real 3D model. You can put your point of view anywhere. So, and if you add camera data, you could even add RGB data to it and make it almost look realistic, photorealistic. I mean. So I think. I think you're getting the idea. I mean, obviously a lot of people say, why don't we use photogrammetry? And I'm sure that's a way of doing some 3D data, and that's obviously a relatively inexpensive way of doing it. But I have to assume that when it comes to real measurements where you really need to know where's your location within the centimeter range, if, for example, if you scan a factory or oil refinery and you really want to know how has it been built, because the blueprint might be completely different than what really is in reality out there, then photogrammetry at larger distances will not be as accurate as a LiDAR measurement that really does measure the distances. This is a company, Routine, in the UK. It's actually out of Scotland. And they developed something similar to what I talked about in the first company. So they have a LiDAR pod. Essentially, they make this little little box on the bottom. It's using carbon fiber material to keep the weight low. And they're mounting it on this Vulcan multi-frame, which is also a UK company, and doing the same thing, looking down, scanning the area. And I'm going to show a couple of pictures out of that. You can see the differential GPS antenna that's here. You see the one side, the other side is back here. Obviously, the higher accuracy you get on your position, on your GPS position, the higher accuracy you get in the absolute point cloud, the relative data will be fine. And see that one in action. There's no sound to this one until it takes off. So you see the pod here with the carbon fiber material. It's obviously done in the UK if you look at the jackets. Very typical for airfields in England and Scotland. There's the scanner scanning. So they kept the opening field very small, not to have anything influence the scanner. And then, of course, it takes off. Here's the differential GPS. I'm going to jump a little bit, as I'm sure you all have seen UAVs flying around. The interesting part is more what comes out of it. Here, very nicely seen. The sensor obviously can be flown in any direction. Let me go a little bit forward because I think there's a section where we actually see the lens, and then you actually see the data, again the real-time data, not the point cloud. So this is kind of done filming off the laptop, the real-time data playing right after the flight. So this is what the sensor sees. So here you see some colons. Here you see a car coming by. Or the car is probably stationary and the UAV was flying over it. Brilliant. And again, now if the data is all being compiled and georeferenced, you actually get a very nice point cloud. The last application I want to show is with exact maps. This is actually very interesting. That's kind of why I kept it to the end. Exact Maps doesn't use a GPS, it doesn't use an IMU, so therefore it is indoor mapping capable, and they're actually doing that right now. And they will be exhibiting at the AUVSI show, which is next week in Florida, in Orlando. They also, one of the things they've implemented is not to store the data on board, but actually to have it completely wirelessly transmitted down. And it's about 2.5 to 3 megabytes per second. That's the amount of data. So it's similar to a high density video stream. And obviously they have a video as well. And to me, that's very impressive. This company didn't have a sensor less than 9 months ago, and this is what they realized. So here's a GoPro camera on there, and our sensor. This is a live view. And then in a second, you see the point cloud that is generated using something that's called a SLAM process, which is a self-localization and mapping. So essentially what it does, it looks into the data and recognizes features, and then from one shot to the next shot, it determines how did these features move, and that's the movement that the UAV did, and that's the movement that's being used to generate the point cloud. So it's a self-referencing process that doesn't require GPS and IMU. From my angle, this is very low. You see the power lines in here. It's obviously flying over a foresty area. And now you see a little bit of a city steam. And look at this advertisement here, for a long time. You're going to see that in a second again. This is the live data, real-time data out of the sensor. And you see that it's a little bit brighter down here. But here you can actually see for a lifetime or whatever it said there, you can actually read that on the side of the wall. And that's because our sensor not only measures distances, it also measures reflectivity. So if there's a high contrast, you're actually being able to pick that up. Specifically, if there's retroreflectors like street signs or something like that, you can filter those out from diffuse reflectors, which are in nature. And that brings me to the end of my presentation. I will be here till this afternoon. If you should have questions that don't get answers after this talk, shoot me an email at lidar@velodyne.com, and I will answer you. But if there's questions right now, feel free.
What's SLAM mean again?
SLM? SLAM means self-localization and mapping. So it's a little bit like if you stand here and take a picture, a 360-degree picture, you take your camera, you point it in one direction, you point it in the next direction, in the third direction, and afterwards you want to put it together into one image with Photoshop. You kind of look into the picture and you see there's a tree on the right side. So in the next picture you want to have the same tree on the left side. And that's essentially what this is, much faster and a little bit more accurate, and looking into 3D data rather than just doing it by hand in Photoshop. Yeah.
Good morning.
Hi.
I'm curious, is anyone trying to, first of all, Stephen Rayleigh from Swift Radio Planes. Is anyone trying to integrate your LiDAR into a fixed-wing airplane?
Yes.
Okay. What's the range of your LiDAR?
The range of our LiDAR is up to 80 meters. We do get signals at 100 meters, but the effective range where you can really still see features is about 80 meters, which of course means if you fly and you're looking down, you can fly to about 70 meters because you also want to see a little bit in the diagonal. Yes, that's the range.
And at the speed you're flying, well, if you were to fly at 18, 20 meters per second, is your LiDAR spinning fast enough?
Yes, so I'm missing that slide, but I can send you that if you send me an email. So if you take an area of 50 by 50 meters, that's the example that we calculated. If you have an area of 50 by 50 meters and you fly at about 20 meters per second, you get a point density of 80 points per square meters. Or in that whole area of 50 by 50 meters, it's 200,000 points in that field that are distributed there. So it's 400 sweeps, and in each sweep, going out about 20 degrees to each side, each sweep you have about 500 points, if I recall that correctly from memory.
I see. Sir, just one more thing. Your data storage. Okay. Sure.
Next, go ahead.
Real quick, from the mapping side, I work with folks like Wolfgang all the time, and one thing that you might want to mention is people don't think about this. The system you have is extremely affordable, and if you go to SLAM processing and dump the IMU, it even gets more affordable. I don't know if you mentioned it, but you might want to mention what your price range is for that.
Yeah,
system.
so the price range, I mean, people know from the big companies that I mentioned that do surveying equipment outside, they are beyond the $100,000 point. Our system is around $40,000. So that's the sensor itself. If you do slamming, you don't need a GPS IMU. Otherwise, you need to add the cost for a GPS IMU. That's typically the precision that's required. That's not required in the sensor. So we really just do an OEM component, and specifically for this industry, where you have a lot of people that are very capable of putting systems together. I mean, all of you probably work in the garage in one way or the other. That's ideal. It's not a complete turnkey system. You need to add the georeferencing either with a GPS IMU or with a slamming process to get the full point cloud.
Hi, good morning. Two questions in one. How many rebounds do you get for each one of your beams? And
say that again.
When you shot, do you only get one rebound back, or you can get
currently
rebounds?
we only get one rebound back, but the question is, which is known as multiple echoes in the airborne LiDAR industry. We're working on that because I get the question all the time. In the mobile mapping in a city, that doesn't matter because a laser beam hits a wall and it gets reflected. The question is if it hits bushes or grass or some tree from the top, you might get a wrong signal from the top of the tree while you're really interested in the bottom of the ground. So now that we start going to the airborne systems, that is a topic, and we're working on the multiple returns. So probably in a month or two we will have that.
Great. And the question of the other gentleman, storage. Does it come with onboard storage?
The system itself, it's just the sensor and the data comes out of it. So you would have to deal with storage or with wireless handling of the data.
Okay. Well.
And as I said, I'm around till about early afternoon, so see me in the back and I gladly answer your questions.
Okay, we're going to take a little break, and instead of taking a 30-minute break, we're going to take a 15-minute break, so go talk to your fellow wizards, and we'll convene back here at about 11:20.